All right, so this video is going to be about the summary of convergence and divergence test for series. And what I wanted to do or address really quickly in the beginning of this video is what the difference between a power series and a series is, okay? So a power series is something we're used to seeing, which is the sum from n equals 0 to infinity of x to the n. And this is 1 plus x squared plus x cubed plus x to the fourth plus ... And this is a series consisting of power functions. So we call this a power series. And this power series represents a function, and this is one that we've done in a previous lesson. So this is going to represent 1 over 1 minus x, which is a sub 1 over 1 minus r, over an interval of convergence. And this interval of convergence is negative 1 to 1, because the ratio, which is x, will converge when x is between negative 1 and 1. All right, well, there's another kind of series besides a power series that is from n equals 0 to infinity of n plus 1 over n plus 2. Okay, and you'll notice that this is not a power series because it doesn't have any x in it. So let's see what happens when I plug in 0. I get 1/2. When I plug in 1, I get 2 over 3 plus so on. You can see this is a series that is just involving fractions here and not functions of x. So this is just a regular series. And this lesson is all about figuring out when regular series converge or diverge. Now you might be asking, why do we care when regular series diverge or converge? Well, the next time that we get together, we're going to talk about the interval of convergence for power series, and that they might converge at the endpoints of their interval of convergence. For example, there are some series that will converge, let's say from negative 1 to 1, and converge at negative 1 but not at 1, or not at negative 1 but at 1, or at both endpoints. And so what happens is when we have to check the endpoints for convergence, we are putting in a number for x, and then it changes it from this power series to a regular series, and thus the need to figure out whether we converge or diverge based on just a series of numbers. Okay, so moving right along. The very first test, and there's 10 of them, the first test is the nth term test for divergence, which is exactly what it states. It makes a comment on divergence, but not on convergence of a series. And this is the test I try first, because guess what? If this test says your series diverges, then you're done, and you don't have to consider any other tests to use for divergence or convergence. So practically, what does this mean? Well, if you read it, it says the sum from n equal 1 to infinity of a sub n diverges if the limit as n approaches infinity of a sub n fails to exist or is different from 0. So I like to talk about things practically because I'm an engineer and that's what we do. Anyway, so the practical applications of this is if the limit as n approaches infinity of your a sub n is not equal to 0, then your series from n approaching, when n equals 0 to infinity, well, actually this is 1 here, 1 to infinity, diverges. So it's saying that your nth term has to not be 0 when you take the limit as n goes to infinity, and then you diverge. Your series will diverge. But does this theorem or whatever say anything about convergence? Well, the answer is no. So practically, if the limit is not equal to 0, it diverges. So what it's saying, in not so many other words, is the limit as n goes to infinity of a sub n, if it's equal to 0, it doesn't say anything about that. So sadly, and I put my little frowny face there, This is an inconclusive test for, I can't spell, but we know that already. Inconclusive for convergence. Okay, once I get going, it'll be better, but we're slow to start. All right, so if the limit as n goes to infinity of your nth term is equal to 0, sadly, this test doesn't work for convergence, so we don't know whether it converges or diverges. We just know it doesn't converge if our limit is different than 0. Okay, so let's do a couple of examples. And so in our examples, the question is converge or diverge? That is the question. All right, so the first one, the sum from n equal 1 to infinity of 3n squared minus 1 over 5n squared plus 1. All right, well, let's take the limit as n goes to infinity of the nth term. Well, this right here is a sub n, so I'm going to put that in the limit notation here, 3n squared minus 1 over 5n squared plus 1. And using our knowledge from pre-cal and putting in a large number, we see that this limit is equal to 3/5, which is clearly not equal to 0. So we can say, therefore, this series from n equals 1 to infinity of 3n squared minus 1 over 5n squared plus 1, we know then this one diverges by the nth term test. And yes, we should comment when we're making a decision on convergence or divergence, we should comment on what test we used. Okay, so let's do another example. Let's say, change it up a bit, and we say that n goes from 1 to infinity of 3n minus 1 over 5n squared plus 1. So I'm just changing the square on the top. All right, so we'll take the limit as n goes to infinity of 3n minus 1 over 5n squared plus 1. And when we take this limit, we see that the degree of the numerator is less than the degree of the denominator. So when I put in a large number, the denominator wins, and this goes to 0, which means, sadly, this is inconclusive. For convergence, or divergence. So we ought to try something else. So that's unfortunate. But that's okay. We have 9 other tests to use. So I always try the nth term test for divergence because if it diverges, then you don't have to worry about convergence or any other tests. So, all right, moving right along. Second test is the integral test. Or no, wait. It's not the integral test. And I don't have a sheet for this one. This one is called the geometric series test. And this one is actually, besides the limit comparison test, this one is one of my favorites, okay? The geometric series test states, if you have a geometric series with ratio r, when the absolute value of r is greater than or equal to 1, we know that the series will diverge. When absolute value of r is less than 1, the series will converge. And what does it converge to? Well, A geometric series is from n equals 1 to infinity of a sub 1 r to the n minus 1. And I've seen it in some books as this sum. So let's write it down. This is n equals 0 to infinity of a r to the n. And these are equivalent. It's just this, when n starts at 0, we'll spit out terms that are equivalent. You just start at 0 versus 1. So we know that this geometric series here that is from 1 to infinity of a sub 1 times r to the negative r minus 1 will converge when the absolute value of r is less than 1. And we've been doing problems like this. And what does it converge to? Well, it converges to a sub 1 over 1 minus r. So you can actually sum those up. Geometric series that have ratios that are less than 1. Absolute value ratio less than 1. You cannot add up or sum geometric series that have ratios that are outside of that zone. Okay, so let's do 2 quick examples. And of course the question is again, converge or diverge? So here's example number 1. The sum from n equal 1 to infinity of e over pi to the n. All right, e over pi. Well, we have to figure out what r is, and that's clearly what r is. So we're going to say the absolute value of e over pi. We have to decide if that's greater than 1 or less than 1. And e is 2.718, and then pi is 3.1415. So this ratio here is less than 1. So we can say this series converges by the geometric series test. And we could even find the sum. What is the sum? Well, the sum is going to be a sub 1 over 1 minus r. And let's figure out what a sub 1 is. When I plug in 1, I get e over pi. So that goes on top. And then 1 minus r, which is e over pi. And let's simplify our double-decker fraction here by multiplying the whole expression by pi over pi. And that means our sum will be e over pi minus e. And that would be the sum of this series that converges by the geometric series test. All right? Perhaps you know where I'm going. Maybe you don't. But I'm going to switch up r. I'm going to put pi on top now instead of e, and then make my ratio pi over e to the n. Well, in this case, r, which is pi over e, the absolute value of that, is definitely greater than or equal to 1 because pi is bigger than e. And so we know that this diverges by the geometric series test. And so what does it mean again by diverging? Oh, I heard somebody in the back. Yeah, they just said, well, Mrs. Muller, it means that I can't add it up. They are correct. All right, so let's do the next test. The next test on our list is the integral test. And I hear some moaning and groaning. The integral test. Yes, we're going to have to integrate, which is your favorite thing to do, I know. Okay. All right, well, the integral test states if f is positive, continuous and decreasing. So there are 3 conditions. F has to be positive, continuous, and decreasing. And the AP people are going to expect that you have checked those conditions, so you need to make a comment about whether f is positive, continuous, and decreasing. For x greater than or equal to 1, and a sub n equals f of n. That means you're creating a function, f of x, and I'll give you an example in just a minute, where a sub n and f of x, the only thing different from them is that where you see n in the a sub n, you're going to put an x for the f of x. But the good news is, and there's always good news, that if you can integrate and it converges, so will the series, and they'll either both converge or diverge. So if the integral converges, the series converges. If the integral diverges, then the series diverges. And that's nice because it's pretty cut and dry. So my first...
Okay, I found this on the web for the series converges.
I say series and Siri wants to talk to me. Right, okay, so I silenced her. I took out her vocal cords. So we'll see if that holds. Okay, here we go. I'm going to give us a famous series here that we're going to discuss, which is the series from n equal 1 to infinity of 1 over n. Okay, this is very famous, and it's so famous it has its own little special name, and it's called the Harmonic series. And I don't know if anybody has watched Mathmagic Land with Donald Duck, but they call it a harmonic series because, yes, it does have something to do with music, and the wavelengths of the overtones of the vibrating string, you know, when Donald Duck plucks the string, the string vibrates, and it has wavelengths, and the vibrating string will have overtones that are in 1/2, 1/3, 1/4 of the fundamental wavelength. And that's all, you know, physics. I know we're screaming when we hear the word physics, but anyway, but they connect it to music because the world's most beautiful music, they find, correspond to the simplest ratios of whole numbers, which is really pretty cool. And obviously 1 over n is going to generate a series like 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. And of course, these are ratios, simple ratios of whole numbers. So there's a whole nother course that could be taught on harmonic series and all of that. But this is a very famous series. And if you use the words harmonic series, the AP people are going to know exactly what you're talking about, that they're talking about this series right here. Okay, but we want to know if it converges or diverges, meaning can we add up all these numbers? Now our instinct would be that, yeah, we can add up these numbers because these are fractions and they're getting smaller. But let's see, we're going to use the integral test. So using the integral test, which means I have to integrate from 1 to infinity of 1 over x dx. Now, why did I choose 1 over x dx? Because my harmonic series says 1 over n. And the integral test says, well, if you have a function that's positive, and if we think about 1 over x, this is why we learn all our toolkit functions. 1 over x, like this, in the first quadrant, from 1 to infinity, is positive, it's continuous, and it is decreasing. So it fulfills all of the integral test requirements. And I take x and put it where the n is, and that's how I created this function. And yes, I hear it now, the moaning and the groaning, but Mrs. Muller, that's an improper integral, and I have to use limits. Yes, you do. We have to use limits. But we love limits because it's nice math language. All right, so here we go. The limit as b goes to infinity of the integral from 1 to b of 1 over x dx. And we have to integrate 1 over x. Well, whose derivative is 1 over x? That happens to be the natural log of the absolute value of x. But x is going from 1 to infinity, so I don't need the absolute value bars, such that we're going from 1 to b. And then when we evaluate, that's going to be the limit as b goes to infinity of the natural log of b minus the natural log of 1. Yes, look at all this great math notation that I know you all are going to use. Okay, so this goes to infinity because the natural log of b is infinity as b goes to infinity. And the natural log of 1, as we know with our properties of logs, is 0. So what do? We can make a conclusion here that we can say, therefore, the integral from 1 to infinity of 1 over x dx, since it goes to infinity, diverges. If it diverges, then what also is true? Well, the series will also diverge. So we can say, and so will the sum from n equal 1 to infinity of 1 over n by the integral test, right? So that's interesting. Well, what makes this interesting is the natural log of x. When you take the antiderivative of 1 over x, you get the natural log of x. And this tends to happen even though this is decreasing, and you might think you can add up all those numbers. The antiderivative of 1 over x is a natural log of x, and it's an increasing function. And so when you integrate and get an increasing function, the odds are very high, probably 100%, that your integral is going to diverge. So that's why that is the case. Okay, I would like to do one other example for this. And the other example I'm going to do is this one. This is number 2. The sum from n equal 1 to infinity of 2n e to the negative 4n squared. And how, the question might be, well, how do I know I'm going to do the integral test? Well, usually I do the integral test when I see something that I can integrate. And when I look at this, the integral that we're going to have to do, the corresponding integral would be the integral from 1 to infinity of, I'm going to put an x where the n is, so this would be 2x e to the negative 4x squared dx. And then I see that if I let u equal negative 4x squared, the derivative of that is negative 8x. And I have an x dx in here, so I can integrate this. All right, so let's see what happens here. The limit as n goes to infinity of, not n, I'm sorry, it's b. b. So the limit as n goes, or b goes to infinity of 1 to b of 2x e to the negative 4x squared dx. And I'm going to do an integration aside over here. You know where I do all my little integration work? There it is. We're going to integrate 2x e to the negative 4x squared dx. And I'm going to bring the 2 out in front. X e to the negative 4x squared dx. And then we're going to let u equal negative 4x squared. Du equals negative 8x dx. Dividing by negative 8, we get du over negative 8 equals x dx. Bringing the negative 1 out, I get negative 1/4. The integral of e to the u du. And we're so happy to see e to the u because we know that antiderivative is just negative 1/4. E to the u. But what is u? Well, u is glad the integration is over. And it's e negative 4x squared. All right, so we're going to bring it back to our limit, and we're going to say the limit then as b goes to infinity of negative 1/4 e to the negative 4x squared evaluated between 1 and b. And I'm going to put things where they belong with that exponent there, because sometimes it's easier for me to see, and perhaps you, if you put e on the bottom when it's got a negative exponent, such that we go from 1 to b. All right, and then let's evaluate using the fundamental theorem of calculus. So we're going to plug in b, which is 1 over 4e to the 4b squared minus a negative 1 over 4e to the 4th. Okay, and then we're going to let b go to infinity. So when I let b go to infinity, this 4b squared gets very large. So this term here is going to go to 0, and I'm left with 1/4 e to the 4th, which is a number, which means my integral converges. So we would say, therefore, the integral from 1 to infinity of 2x e to the negative 4x squared dx converges, and so will the series that it's associated with, which happens to be the integral from, the sum from n equal 1 to infinity of 2n e to the negative 4n squared. Now, I didn't check to see if this was a positive, continuous and decreasing function, this 2x e to the negative 4x squared. But I will let you verify that on Desmos. But think about it, e to the negative 4x squared, e to the 0 is 1. So it's going to start up here and then, I think come back down. But we'll verify that at a different time, because this is just a summary of the tests. Okay, so we're on now. P-series. Siri again is thinking.
Sorry,
I know. This is hilarious. This is absolutely hilarious that she just thinks I'm talking to her. What are we going to do about that? We're just going to turn her off. There she is. She's officially off. Voice box gone. All right. P-series. Yeah, it's not a funny name, P-series. But the reason they call it a P-series is that we're going to have a series of the form, the sum from n equal 1 to infinity of 1 over n to the p. So the exponent is p. All right? And so the P-series test states that if p is greater than 1, the series will converge, and it will diverge for p that is less than 0 but less than or equal to 1. And the classic P-series is what we just proved, which is the harmonic series here, which has p equal to 1. And we just proved that this one diverges. And what test did we use? Well, we used the integral test. So there are more than, you can prove convergence using multitudes of different tests. It's just maybe one test might be easier to do than another. And you'll see that most people like the P-series test because of this form, it is one of the easiest ones. So let's remember that this series will converge for p greater than 1, and it will diverge for p between 0 and 1 inclusive. All right, so let's do some examples. All right, so we're going to do the sum from n equal 1 to infinity of 1 over n squared. And what is p in this case? Well, p is 2. So if p is greater than 1, we know that this converges due to the P-series. It's a P-series with p greater than 1. And that's all you have to do to state or talk about convergence, because p is greater than 1, right? Because p is 2. All right, so that's example 1. I can tell you're liking this test already. Me too. All right, so the next one, let's do another one. N equal 1 to infinity of this series, 1 over the cube root of n squared. Well, sometimes it's not necessarily clear until you change to exponential form here. So we're going to go from n equal 1 to infinity of 1 over, this is the cube root, so this is n to the 2/3. Well, 2/3 happens to lie between 0 and 1, so we know that this series diverges because it's a P-series, and that P-series is less than or equal to 1 in this case. All right, easy stuff. All right, let's do one more example. The sum from n equal 1 to infinity of, let's flip the fraction around. Let's say it's 1 over the square root of n cubed. And that's going to equal the sum from n equal 1 to infinity of 1 over n to the 3/2. Well, now this has flipped this fraction, and this fraction is now greater than 1, so we know that this series converges by the P-series, p greater than 1. All right, so that's the P-series. Most famous P-series of all is the harmonic. All right, moving right along. Next test. The next test is the direct comparison test. Now, this is pretty logical, I think. So let's read it. It says, if you have two sequences, A and B, and one sequence, B, is bigger than or equal to A, but both series are greater than 0, which means this is an implication, right, that the series are positive. Okay, so what the direct comparison test states is if B converges, if the series for B converges, then the series for A will converge. Well, let's see if that makes sense. B's values, B's terms are all bigger or equal to A. So if B converges, it's bigger, then guess what? A is smaller, so we should be able to add it up so they both converge. And then the second direct comparison would be if I said A diverges. Now remember, A is smaller than B, so if A is smaller than B and A diverges, you can't add it up. If the terms are bigger, you really can't add it up. So if A diverges, so too will B. Okay, so I'm going to do a classic example here. Here's an example. Let's say we have the sum from n equal 1 to infinity of 1 over n cubed plus 1. I like to call this test the "oh, I wish something was different." And in this case, "oh, I wish that 1 happened to be gone." Because if it was gone, I'd have 1 over n cubed, which I know is a p-series and converges, right? So let's compare this one directly to the series from n equal 1 to infinity of 1 over n cubed. All right, well, so we have to decide now if 1 over n cubed is bigger than 1 over n plus 3. N cubed plus 1. Well, if I have a bigger denominator, then this one is smaller than this one. So I know that I can say this one converges because it's a p-series with p greater than 1. And what else do we know? And we know that 1 over n cubed plus 1 happens to be less than 1 over n cubed. So, and for all n, right? We should state for all n. For all n greater than or equal to 1 here. So since we know that this one converges and the terms are of the series I want to compare it to, I can say by direct comparison test, right? Because I can use the abbreviation for direct comparison test, DCT. I can say by comparison, the sum from n equal 1 to infinity of 1 over n cubed plus 1 also converges. Okay, so that's an example for the direct comparison test. So for the direct comparison test, you have to know one that either converges or diverges to compare it to the one that you don't. All right. Now, the next one is also a comparison test, but I like it a lot better because it compares the limit as you put your nth terms, the ratio of your nth terms. So you're going to put a sub n over b sub n, or if you do b sub n over a sub n, it doesn't matter. But they're either going to both converge or both diverge. And the reason this works is we've seen a ratio before where we put a function over another function, which was related rates of growth. So I want you to think related rates of growth. And remember, when we did related rates of growth, what did we do? If we had a function over another function and we took the limit as x went to infinity and we got infinity, that meant the function on top was growing faster than the function on the bottom. And if the reverse would be true, if I had the limit equaling 0, then the function on the bottom was growing faster than the one on top. Well, what happened when we did the limit as x went to infinity and we got a number, a fixed finite number? Well, we said, well, it grows at the same rate. So if things will grow at the same rate, that means they're going to behave the same. So if they're behaving the same as n goes to infinity, then they're either going to behave the same convergently or divergently. Okay, so this again, we have to know one that we want to compare, whether it converges or diverges. So let's choose the harmonic. So I'm going to choose n equal 1 to infinity, and I want to know if n plus 1 over n plus 1 converges or not. So what am I going to compare it to? Well, I'm going to compare it to one I know, 1 over n, because I know this one is harmonic and diverges by the either the integral test or the P-series test. So let's see, we're going to take the limit as n goes to infinity of, and it doesn't matter which one you put over each other, so let's just put 1 over n over 1 over n plus 1. It really doesn't matter because the ratio will be either a number, it will be a number or it won't be a number no matter which direction you do this, okay? So this will be the limit then as n goes to infinity of n plus 1 over n, and this equals 1. Well, so we got a number that was finite and positive, right? So L can't be, we've got to know this, L can't be 0 or any kind of infinity here, okay? But we got a number. So what does that mean? That means these two functions grow at the same rate, which means they will either both converge or both diverge. So we have to make a statement. We have to say, since the sum from n equals 1 to infinity of 1 over n diverges, and how do we know that? The P series, P equal to 1, and the limit as n goes to infinity of 1 over n over 1 over n plus 1 equals 1 by the LCT, the limit comparison test, both will diverge. Okay, and sometimes you have to use L'Hopital, but in this case it worked out where we didn't. Okay, so those are the two comparison tests, and I really like the limit comparison test better, so that's a personal preference. All right, let's do the next one. Next one is the ratio test, which we are all familiar with, finding intervals of convergence and radius of convergence. So I'm going to quickly do an example here. I always use the ratio test when we have factorials involved. All right, so let's do an example, because I'm about to run out of time here. So the sum from n equal 1 to infinity of 4 to the n over n factorial, using the ratio test. That means we're going to take the limit as n goes to infinity of absolute value of a sub n plus 1 over a sub n. And that just means we're going to take and put n plus 1 in where we see n, and then create a fraction. All right, so this would be 4 to the n plus 1 over n plus 1 factorial divided by my double-decker fraction, 4 to the n over n factorial. And I'm going to change flip here. So we get the limit as n goes to infinity of 4 to the n plus 1 over n plus 1 factorial times n factorial over 4 to the n. Okay, and as I have often said, inside n plus 1 factorial is an n factorial waiting to be canceled. So there we go, we're going to cancel the n factorials. And 4 to the n cancels with the n up here, and I'm going to get the limit then as n goes to infinity of 4 over just n plus 1, and this goes to 0. Okay, and with the ratio test, if your limit turns out to be less than 1, then you know your series converges. Okay, so sum from n equal 1 to infinity of 4 to the n over n plus 1 converges by the ratio test. Yay, hallelujah. Okay, so let's talk about when it doesn't converge. Well, it doesn't converge when your ratio or your R is either greater than 1 or infinity. Now, I suggest to you that infinity is bigger than 1, so they could have just said this, but anyway. If you get a ratio test that equals 1, sadly, that is, here's my frowny face, inconclusive, and you got to try a different test. Okay, but typically I use these when you see factorials. Okay, next one is the root test. This one is not used very often, and the root test just is what it's implied. You're going to take the nth root of whatever your a sub n is, okay? And when do you use this test? And well, you use this test, for example, this is number 73 from the book. So part A. So we're going to say the sum from n equal 1 to infinity of n squared over 2 to the n. And you see how we have a polynomial over an exponential here. And that's kind of an indication that you might want to use the root test. Now the root test has the same conditions as the ratio test. If your root test limit turns out to be less than 1, then it converges. If it's greater than 1 or infinity, it diverges. And if it's equal to 1 again, you have to try a different test because it's inconclusive. Inconclusive. So let's do it. Here we go. So this is the limit then, as n goes to infinity, of the nth root of, now this says absolute value here, but my terms are positive, so I don't have to show that. So I'm going to say n squared over 2 to the n. All right, you can rewrite the nth root as in exponential form and say n squared over 2 to the n raised to the 1 over n. And when you do that, I can now distribute the exponent, and we get the limit as n goes to infinity of, this is going to be n to the 2 over n over 2. All right, and that is, everybody's going to say, well, that's going to go to n to the 0. Well, but n is in the denominator too. And you got to use L'Hopital's rule, because the limit as n goes to infinity of n to the 2 over n is really of the form infinity to the 0. So we'd have to say y equals natural log of y equals the limit as n goes to infinity of, bring the 2 over n down in front, natural log of n. And I need to get a fraction, so this is the limit as n goes to infinity of 2 natural log of n over n. And now this is infinity over infinity, because as n goes to infinity, the natural log goes to infinity, and so does n. So I can use L'Hopital's rule and say the limit as n goes to infinity of 2 times the derivative of the natural log of n, which is 1 over n, over the derivative of n, which is 1. And now I can say the limit as n goes to infinity is 0, but I have to bring the natural log down. This is the natural log of y. So we exponentiate both sides, and we get y equals 1. So this limit right here is equal to 1. So this goes to 1/2, which is less than 1. And I can say then that the sum from n equal 1 to infinity of 2, or of n squared, of n squared over 2 to the n converges by, the root test. And the root test says convergence if your limit is less than 1. All right, alternating series test. This is otherwise known as Leibniz's theorem. He actually has a theorem named after him. Newton gets all the glory sometimes. So this applies to alternating series. Now, how do I know if a series is alternating? Well, this is the telltale sign right here. Do you see this? That's an alternating piece. So the alternating series test is really pretty simple. And this is saying that the non-alternating piece, the a sub n's in here, are all positive. All right? But I like to guarantee that by saying absolute value bars here and here and here and here. Okay, so that's my preference. So it says this series will converge when the two conditions listed below are met. Okay, so let's do a classic one. I'm going to do this one, -1 to the n over n from n equal 1 to infinity. This, my friends, is the alternating harmonic. And it's harmonic because it's a p series with p equal to 1. All right, so it's alternating, right, because it's got the alternating piece. So let's do the test. Part 1 says, well, the limit as n goes to infinity of 1 over n, absolute value of that, has to go to 0. Well, yay, it does. That's the first check. The second one is the terms here have to be getting smaller because this states that the n plus 1th term better be smaller than or equal to the nth term. So let's plug in n plus 1. So I'm going to have 1 over n plus 1. Is that smaller than or equal to the nth term? The n plus 1th term? Now I have a bigger denominator here, so that's going to be a smaller fraction. So yes, it works. So I can say then the sum from negative 1 to n over n, from n equal 1 to infinity, converges by the alternating series test. And you can use AST here, alternating series test. Now what's really cool about that is this works for alternating series if these two conditions hold, which is pretty cool. Now, if the two conditions aren't met, you might have to try a different test. Okay, so be careful of that. All right, so the last thing I need to talk about is something called absolute convergence. Absolute convergence. Now, absolute convergence is a really simple subject here, okay? And I'm going to give you an example really quickly. The sum from n equal 1 to infinity of negative 1 to the n over n cubed, all right? So this absolute convergence states if the absolute value of its terms converges, then the series without it will converge, meaning the alternating maybe piece will converge, okay? So let's check the absolute value. What happens when I take the absolute value of an alternating? Well, that's going to just be 1 over n cubed. So this will be n equal 1 to infinity. And so I know that this converges by p series, p greater than 1, right? Because p is 3 and it's greater than 1. So this converges. So the absolute value of this converges. Therefore, the sum from n equal 1 to infinity, negative 1 to the n over n cubed converges. So since the absolute value of it converged, the alternating will converge because it'll be a smaller series because I have a positive term, negative term, positive term, negative term, positive term, negative term. When you add those up, that'll be smaller than just adding up the absolute value of all the numbers. So I hope that makes sense. And if this condition happens, they call this absolutely convergent. This series right here is absolutely convergent because its absolute value converges. Okay, we have another series that's famous, n equal 1 to infinity of negative 1 to the n over n. This is the alternating harmonic. Okay, the alternating harmonic, which we just proved, I think. Did we not just prove that the alternating harmonic, we just proved just a second ago that the alternating harmonic converged. But what do we know about the absolute value of that? If I take the absolute value of that, my E's are looking really bad. Sorry, my sums. Those S's. N equal 1 to infinity of 1 over n. We know this diverges by the p series. P is equal to 1. Okay, so the absolute value of it diverges, but the alternating harmonic converges by the alternating series test. So we call this series here conditionally convergent. Why is it conditionally convergent? Well, it's convergent conditionally because it's convergent on the condition it alternates. So conditionally convergent functions are typically alternating functions that do not converge when their absolute value diverges. Okay? All right, so that's all I have for this lesson. I know it was pretty quick there towards the end, but I was starting to panic with time. I hope you guys have an incredibly blessed day, and we will talk more about series the next time I see you.